we're looking at here is a AP Physics C E&M question from 2003. It's question number 1, and it deals with Gauss's law. If you've been looking at the prior videos in the YouTube playlist, we've done a bunch of Gauss's law. It's a guarantee that on this test you will see a Gauss's law problem. This is just one of the harder versions of it for a fact that we have a non-uniform charge distribution. So we've taken a look at that little twist of the problem here. What we've got, though, if we kind of look at this, is a spherical cloud of charge of radius r, and it's containing a total charge of plus q. So this whole thing's got a charge of plus q on it, and it has this non-uniform volume charge density. Okay, and that's a very, very important thing for this problem and make things a little bit weird. And it varies according to this equation. Rho of r, so the density as a function of radius, equals rho naught times the quantity 1 minus little r over big R. And that's for whenever we're inside the cloud, for little r is less than or equal to big R. And the density is 0 when we're outside the cloud, so nothing exists outside this cloud. Okay. We're looking to express all algebraic answers in terms of q, r, and fundamental constants, so epsilon naughts and whatnot, and pi's. We're not really going to see this piece here, that rho of r, that density function, until we get to parts D and E to this problem. Before that, those problems are actually pretty straightforward, and you can do this if you've done any of the other Gauss's law problems here. What we're looking at to begin with is what is the magnitude of the electric field when we're at a r value greater than r. So whenever we're floating, somewhere out here in space, what is the electric field somewhere out here? And if we've been doing some of these other Gauss's law problems, this should be a straightforward answer for us. Since we are outside of all of the charge, this plus q, we can treat all of that charge for the spherical distribution as being a point charge, as existing at one point in space right there. So as long as we know the equation for an electric field, this is really straightforward here. All we have to say is that an electric field equation for a point charge is just equal to kq over r squared. And then in our case here, we know that the total charge we have in this scenario for our charge is that positive q. So this equation just becomes k, here's our positive q, that's the total charge we had, divided by r squared. Woo! That was it. That was 2 points. Way to go for us. And that's just for recognizing that this is a spherical charge distribution. We are outside of that spherical distribution. We're going to treat it as a point charge. And we've done that a lot so far. We want to find the electric potential for those same positions being outside of R. So what is our electric potential, or our voltage out here? And if we're doing voltages, it's the same idea. We treat this entire charge distribution as a point charge, as existing at one point in space. And all we have to say here is that the voltage is equal to k, the charge that we have, q, and then the difference for the voltage is that's that r squared value. Okay. You could technically also do this by integrating your electric field. You can do that as well. That's totally fine. This equation is just sitting on the equation sheet for this test, so you might as well use it. Okay. The key here is remembering that spherical charge distributions, when you're outside of the sphere, act as point charges, and that's a nice thing for us. What we now have to do is, in part B, we have a proton. It's placed at point P, so we take a proton, we put it right here, and we're asked to just describe its motion for a long time after it's released. Well, if all of this is positively charged, and this is a proton, so it is positively charged as well, there are a few things we can say about it. We know that since these are like charges, this proton is going to move away from the sphere. Okay, so it moves away from the sphere there. That's the first thing we can say. The second thing we can say is that as this proton is being moved away, since there's a force being applied to it, that Coulomb's law, F equals kqq over r squared, we know that the proton is going to speed up. Okay, so we know it's going to speed up. So we could say that its velocity is going to increase. Now, while we can say its velocity is increasing, at some point, it will kind of reach its final velocity. It'll kind of reach some limit at which that's the speed it's going to be traveling. And the reason this occurs is because as this proton moves further and further away, the force acting on the proton is going down. If we take a look at Coulomb's law real quick, the force acting here is equal to K, Q, and then one of these Q's is the big cloud, over R squared. As we get further and further away, that force acting on the proton goes down. And remember, this equals a mass of the proton times the acceleration. So since the force is going to be going down as it gets further away, that means the acceleration will be decreasing as well. So the third thing we can say here is that the acceleration is decreasing as this moves further and further away. And because that acceleration is going down and down and down, eventually that acceleration will approach zero as this R value approaches infinity. And when your acceleration is zero, you're no longer speeding up. Now, it'll never actually reach zero. It's all a limit in that regard. But that's the idea of what will be happening here after a long time, because that's what they're asking for. So we can say that one thing that happens is the proton moves away from the cloud. The second thing that can happen is the proton will speed up. Its velocity will increase to some max velocity. And that's because our acceleration is decreasing. And those are the three things we can say about it there. Okay. For part C, we're asked to take an electron and it has some charge magnitude. I don't know if they want that A to be the charge magnitude, but it could be a typo. I don't know. It's an electron though. It's placed at point P. So we take that proton that existed there and we say we don't want to deal with it anymore. We want this to be an electron. So we place an electron at point P, and it's a distance r from the center of the sphere, and it's released. We need to determine the kinetic energy of the electron as a function of r as it strikes the cloud. So as this electron is falling inwards, what is its kinetic energy at that point right here? So this is just a conservation of energy thing that we have to deal with. What we basically need to be thinking about here is that our initial energies, whether they be kinetic and potentials, have to equal our final kinetic energies and our potential energies as well. The way that we could do this, I like to just write out the entire kinetic energy equation. So what I would write out is that, or the conservation of energy, I like to say K initial plus the potential initial equals the K final, the kinetic final, plus the potential final. And I know initially my electron is at rest, so this is zero, it goes away. And that means I can write that my final kinetic energy, what we're looking for, is just the final potential energy, or excuse me, I wrote that wrong. My final kinetic energy, if I subtract this over, is just going to be my initial kinetic, or my initial potential minus the final potential. What we need to do then is we need to think back to what is a potential energy of a point charge system. Remember, we're outside the sphere at this point, so it's still point charges. And we can think of a potential energy as equaling K QQ over R. Now, the one weird thing about this that we have to note is that when we're talking about coming in from infinity, all of our potentials, infinity is at zero, so all of our potentials here are technically negative. So when we do this, and we're writing this equation out, we're going to have a negative K, and then we need to put the charge of that electron in there somewhere. It just has some magnitude. We'll just type it as E, because it's just an elementary charge. And then this is our big Q of the entire system here, over little r, because that's where we are initially. We're at some distance on the outside. And then we are subtracting from that, because we got a subtraction sign right here, minus a negative k e q over, and this is where we are when we end, and we are at a position of big R. So now it's just a matter of kind of reworking this out. We see that we've got subtracting a negative sign. That's like the addition idea. So we can just say that this here is a positive, and I'm going to take a K, E, and a Q to the outside because those are like terms. So here's a K, there's an E for the electron, there's a Q, and then because that is now 1 over R, it's the positive minus, because that's the negative, 1 over little r. And that's an energy conservation problem right there. So it's very similar to stuff you may have done in mechanics where you're just conserving potential and kinetic energies. There's another way we could technically do this problem if you wanted to. You could think about this as the kinetic energy is equal to the amount of work done, which if you want to think this as a more calculus based, you could call this the integral of the force dotted through some distance. In our case here, the way that would look like is it would be the integral going from some initial position little r to some final position big R, and then we'd have to list our force in there. Our force is Coulomb's law, so that's going to be our KQQ, so K, there's our E for the electron, and it's negative, so that's a negative quantity, Q, and that's over R squared. Whenever you do this, you get the exact same thing when you integrate. You end up getting the final result of KEQ times the quantity 1 over big R minus 1 over little r. There's a little bit of algebra that goes into that. Okay, I'm going to leave that as it is though. I really think for a problem like this, there's no reason to be dealing with the integration or fumbling over it if you forget it or you're new to it. It's a little bit easier in this problem just to remember how to conserve energies and call it a day. But if you wanted to, that's how you could do it. Okay. For part D, this is where things get interesting. This D and E right here, these are the hard parts. This is the new stuff. This is what we're here looking at this specific problem for. And just so you know, between parts D and E, there's only 6 points floating around. So if you get down to this part and you feel confident and you're like, I don't know how to do this, you just got 9 out of the 15 points for this question. Flip, go on to something else. Figure out question 2, figure out question 3. See what you can get there points-wise. Then come back to this, because this is where the kind of harder stuff is. And if you haven't been practicing these problems or you haven't watched this video all the way through, then that's going to be difficult for you. Okay? But what we're asked to do for part D is to derive an expression for rho naught. What is rho naught? The initial density of our function. So what we have to do here is we have to combine two ideas. We have to combine the idea that we have a density function. And the other idea that we have to think about is that this sphere has a total charge of positive Q. And what this means is that if we add up all of the charge, which is spread out according to this charge density, it's some density per unit volume. But if we were to add up all of the volume and all of the bits of charge that it has, because there's some density, then we would get, in the end, the total charge out of our system. And our total charge here is plus Q. So what this means is if we're adding everything up of this changing function, is we're going to be stuck with an integral here. And there's no ifs, ands, or buts about that. But what it means is that when we write this, we can say that our integral, because we're adding up a bunch of things, from the center of the sphere at point 0, going radially out of that sphere to some radius big R, that's going to equal, or we're gonna integrate that over the density that we have. A density is a function of R by a volume. And the way you can kind of think about this, and I'll draw this like way over here because we may need the space, is if I have some sphere that starts at 0 and goes out to big R, what we're essentially doing is we're saying, look, let's take all of the density throughout this region right here, and let's figure out that density multiplied by the volume of that little sphere. That's going to give us some charge. And then we're going to take the next piece, and how much charge does that give us? And then how much does that give us? And how much does that give us? Because what we're doing here is we're moving outwards through some dr value, okay? So this means that even though we're integrating a volume here, a dv, we need to be careful about what this dv represents. This dv for us actually represents a surface area of a sphere, 4 pi r squared, multiplied by some tiny infinitesimal dr distance here, dr. And the way you can also think about that is if you integrated like both sides of this, the dv and the 4 pi r squared dr, this would give you a volume, and this would give you 4/3 pi r cubed, which that's the volume of a sphere. So this we can remember, and with that we can get back to this idea of dv. And this is so important because this is actually what we're going to plug into this equation. And that will give us the entire charge contained in this sphere, which we already know has to be equal to positive q. That's the total charge contained there. So let's write this out and see what happens here. So we're going to have q equals my integral from 0 to r of, and then here's our function. Our function, rho of r, is rho naught times the quantity 1 minus r little r over big R dv, which is actually 4 pi r squared dr. That's what we need to integrate. Now it starts looking like that, and it looks a little bit complicated, but there's actually a lot of things that we can pull outside of the integral because they're constants here. Things we can pull outside are the 4 and the pi and the rho naught. We can just whoop, get them all out. So what we'll do here is we're going to do just that. We're going to pull all of these things out here. So this integral is now going to look like 4 pi rho naught times the integral from 0 to big R of the quantity. And then I'm going to distribute this r squared to both the r and the 1. So this is going to look like r squared minus r cubed over big R dr. And that's just a polynomial that we can integrate. That's nice and straightforward for us. If we remember our integration rules, we're going to add 1 to these exponents and then divide by our new exponent. So whenever we do this, we're going to get our constants in front again, so our 4 pi rho naught. And then now we don't need to worry about the integral because now we're integrating. Adding 1 to that exponent gives me r cubed, and then we divide by that exponent over 3, minus adding 1 to the exponent gives us r to the 4th over 4, because we divide by that exponent. And then we still have this big R here, so we need to bring that through. Okay. Don't forget, we still have our bounds here. We're integrating from 0, nothing, to the radius of the sphere itself, big R. And what this means is that we're going to have to put this big R and the 0 in for the little r values whenever we do this. This gives us 4 pi rho naught. Plugging in the big R values gives us big R cubed over 3 minus big R to the 4th over 4R. And then technically speaking, there'd be a minus 0 over 3 minus 0 over 4R, but 0 is 0, and 0 minus 0 is 0, so we don't need to worry about the rest of it. And this is what we're given here. Technically, I think you're fine leaving that. You get full credit with leaving that on a test. If you want to just work it out so that things look a little bit nicer, we can do so here. Because technically, we need to go ahead and solve for rho naught. Because remember, all of this equals, in the end, big Q. If we wanted to do this, we can see, let's see, we need to work this down into something a little bit prettier. We can do that by getting rid of one of those big R's. So now we've got r cubed minus r cubed values. That's nice. And if we do least common denominators by cross multiplying and kind of doing factors in the bottom, we can see that we're going to get 4r cubed over 12 minus 3r cubed over 12, which is going to give us r cubed over 12. So that gives us 4 pi rho naught times the quantity. Here, I'll just write this out real quick so we can see it. I'll bring the 4 up, so that's 4. That becomes a 12. There's my 3. This becomes a 12. 4 minus 3 is 1. So I'm going to get r cubed over 12. And this equals q, which means that I can say that rho naught equals 12q over 4 pi big R cubed. And that's what we want in the end there. Oh, and I guess I might as well just reduce this. I've got 12 over 4. 12 over 4 is 3. So 3q over pi r cubed. That's a full answer there. You could leave it as 12 over 4 if you want. There's nothing wrong with that. But there it is, 3q over pi r cubed. Whew, that was a lot just to get a rho naught. In the end, it was actually just one integral and doing some math, but you can see how that quickly becomes a lot there, okay? Interestingly enough, you need to do D in order to do part E. If you get part D wrong, that's totally fine. Just take your answer, whatever it is, and just whoop, flip it down here. You'll get some continuity points. There's still some points we can pick up here without really doing anything. So let's try that. What we're trying to do now, though, is before we are outside of that charged sphere and we are at a distance little r greater than big R, now we're inside of it. And this is where things get a little bit more difficult because we needed that rho naught above. While we're inside of this, because our charge amount is varying as we move throughout the sphere, we need to look at an integration technique and we need to understand how that charge density is moving during that sphere's position. In the end, though, this is still a Gauss's law problem because we're looking for an electric field within some charge distribution. So the first thing that we should do is list that the closed integral of the electric field dotted with some area, that's going to be our sphere because we're in a spherical distribution. We've done a lot of these. That's going to be equal to the charge enclosed over epsilon naught. That right there is always a point, okay? The only difference in this problem, and we've seen this in some other problems, is that this charge enclosed becomes a little tricky. This charge enclosed here is going to be dependent on where we are in that sphere. So what we need to say here is that this charge enclosed is going to be equal to some integral from 0 to some position r of our charge density and the volume that we're enclosing within that integral. Okay, so we see that this is very similar to what we did above, except above we had this value q, and now we're solving for that value q. And we can do that now because now we have rho naught, and we're able to do that. So essentially, we can quickly write the left side of Gauss's law because we know what that's going to become. This is just going to become E, and then because we're using a sphere enclosed within our Gaussian, as our Gaussian shape, you know, we're somewhere in here, we're just saying, look, I've drawn a sphere in there. We know the surface area of our sphere is going to be a 4 pi r squared, but the rest of this we need to go ahead and solve for. So we'll bounce over to here real quick and look at this. When we're looking at this, we need to once again think about this integral from 0 to little r this time because we're going to some position in that sphere. And if you remember, our density function was rho naught 1 minus little r over big R. Well, we know what rho naught is now, so let's put in what rho naught is so we can get some charge values. That's going to be 3q over pi big R cubed times the quantity 1 minus little r over big R, and then we've got this dv. And remember, just from before, we're not going to put dv in there, we're going to put this 4 pi r squared dr, because we're looking at things as a function of the radius. So here's our dv as 4 pi r squared dr. So this is the integral we have to do to find the charge enclosed. That's the tricky part of this problem. If we can do this integral, we win. We have everything. So let's figure out what are constants we can bring to the outside. Well, I've got 3 is a constant, q is a constant, pi is a constant, big R cubed is a constant, and the 4 pi are constants as well. So that's a whole bunch of stuff to bring to the outside, but let's go ahead and do it. Cleaning up real quick though. Pi's are going to divide out. That's nice. And 4 times 3 is 12. So I'm going to write this as 12q over big R cubed. Yeah, big R cubed times the integral from 0 to little r of, and then moving the r squared into both of those, the quantity r squared minus r cubed over big R dr. Let's go down here to look at the next part. Okay, so if I want to integrate this, remember just like before, add 1 to the exponent and divide by it. So I'm going to have 12q over r cubed, because that's our constant, doesn't change, multiplied by the quantity of, here's the integral, r cubed over 3 minus r to the 4th over 4r, and then we are integrating this from 0, some interior point, that center of the sphere, out to some point little r here. So interestingly enough, when we put in the little r, it stays exactly the same, and when we put in the zeros, nothing happens there. So this in the end will just become 12q over r cubed times the quantity of r cubed over 3 minus r to the 4 over 4r. If we wanted to, we can clean this up because it's probably best to do so. Cleanup can be finicky at times, but let's do it. Let's cross multiply the 4 and the 3 over, so we get something that looks more like 12q over r cubed times the quantity of well, let's do this. Let's pull r cubed to the outside because r cubed's in there. So pull an r cubed out. So this is going to just be 1 over 3. Oh, let's just, okay. So 1 over 3 minus r over 4r. And then if we common denominator this to make them 12s in the bottom, then we can say that this becomes 12q r cubed over big R cubed times 4 over 12 minus 3 little r over 12 big R. And that allows me to pull a 12 out there and there. And since I pulled a 12 out, the 12s cancel or divide out. And that means what I now have in total, because remember, this here was just the charge enclosed. Oh, a lot of math for charge enclosed. This is just, remember, the electric field times 4 pi r squared equals this whole thing. So q r cubed over big R cubed times the quantity 4 minus 3r over big R all over epsilon naught. So I'll just toss the eps naught down here. Whew. Those go away. Divide by the 4 pi. And we finally find, after much work, that the electric field as a function of r being less than big R, equals qr over 4 pi epsilon naught. And remember, that's actually equal to k there, 1 over 4 pi epsilon naught. Big R cubed times the quantity 4 minus 3r over r. For r is less than big R. Oh, wow. That was a big one. So E is a function of R. That was a big one. That was a lot of work to find that. But in the end, it all stemmed from this initial piece here, Gauss's law. It was just, what is the charge enclosed? All of that work there that we did at the end, like all of this, all through here, and all of that, that was 3 points. So if you know what you're doing and you can do it fast and you're good with the calc and you've got some time, go ahead, go for it. If you're like, hey, I've got other things to do, that is not my biggest concern at the moment, go do other things. Come on back to this question later on, okay? Because as we saw in this problem, there were much easier things to do. The very first question here, where we're just saying point charge and point charge, that was worth a total of 3 points. This right here was worth as much as the very last thing we did, okay? So get the easy points, get the low-hanging fruit, get what you know real quick, move on, come back to do the hard stuff later, okay? You're not trying to do everything. You're trying to get points where you can, okay? But with that, though, this was a non-uniform charge distribution. It had us start integrating over a density or a volumetric density here to start figuring out what is our rho naught, what's our initial condition for our density, and how much charge is enclosed when we're inside that sphere, okay? But with that, this problem is finished. Take it easy, everybody. Make sure you're looking at the prior Gauss's law problems if you haven't yet, because this one builds off of everything we've done. And you have a good one. Have a good winter break. Adios.